So till now we spoke about normal distributions, probability density functions, and probability density functions were really just like graphical representation of the likelihood of obtaining a certain value, or in other words, the probability of obtaining a certain value. When we looked at the cumulative distribution function, we spoke about the probability of obtaining a value equal to or smaller to x, right? So because it's a probability value for short, we can call it a p-value, and you're going to hear p-value a lot. And like we were saying the whole time, this is a really important component of hypothesis testing, because we now have a statistic, a number, say a t, and we can compare the t we've calculated to a range of t's, and we can work out the probability our t is equal to or smaller, or the inverse, larger than the t's in the distribution of population of t. Now, when I talk about the population of t's, we're going to, next slide already, we're going to understand what I mean by having a population of t's. So say, I'm going to not talk about the population of t's for a moment. I'm going to talk about the population of differences between two populations. Okay? So let's not talk about the t statistic. Let's just talk about a difference. There's a population of elephants, and there's a population of hippopotamuses. Right? And elephants are heavier than hippopotamuses. How do we know? On average, the elephant is heavier. It's about 6 tons. The hippopotamus is about 4 tons. So really what will happen is I can take a subsample. Of course, I cannot sample the entire population of elephants. I cannot sample the entire population of hippopotamuses. But what I can do is I can take a group of hippos. I can subsample the population. If I now have a population of samples, and if I sampled correctly, I have a representative population of samples, or a population of samples that is representative of the entire population. If I've sampled incorrectly, if I've introduced biases, for example, if I've only caught those hippos that I can catch because they're small enough to fit in my band, then of course I'm not getting a group representation. But like, okay, so now I'm assuming my population of samples is representative of the population itself, then of all possible, of all possible, oh my God. I can take my population of hippos and weigh them, and I can take my population of elephants and weigh them, right? And I'll have a spreadsheet that has all the elephants. Elephants, hippos, and a list of values, right? So this one's 6 tons, this one's 5.9, this is 6.1, and so on and so forth. Here I have 4, 3.9. And I'm going to get differences in the weights in that mean. And I'm going to have some sort of mean difference of a certain number, of a certain x. But actually, if I sampled a different hippo or a different elephant, that x can vary a little bit. How much? Well, I'm assuming it's normally distributed. There's some sort of confidence I have around what my mean is. So if it's looking normal, here's my mean. I can measure my standard deviation of the sample. I can actually work out the distribution of differences. So this is the difference I measured. Say it was 1.9 tons. It could be 1.8. It could be 1.7. How much this varies, right, depends on the standard deviation. But there is a point where I decide, actually, this is my confidence interval around the mean. This is what I consider to be the mean difference between the populations. If I have a mean difference between my my elephant and this other animal that's like 5 tons, which is way out here, I'm going to say, actually, that animal is not a hippo. Okay, this is a different population altogether. So really what I'm talking about is that probability value. These are the probabilities that I'm going to get a difference of this magnitude. Okay, and this is where p-values are coming from. This is an example that has nothing to do with the t statistic, but it's just to kind of bring it down to something that we all understand a little bit better. So I can define a value. I'm going to call it alpha. I can define a value here that is the value of the p-value that above which I'm going to reject this point belonging to this population. Okay, like we said earlier, we're using an alpha of 5%. Other disciplines use alphas that are slightly different, but I mean, everything is kind of subjective, but is the field's, I don't have the word for it, but you know what I mean. So we have a p-value, a probability of 5% or lower. Okay, so if the p-value is low, the null must go. Because remember what we said, a null hypothesis is everything from the same population. We're always talking elephants and hippos. But actually what we're seeing here is, no, this point, no, it isn't. Okay, p-value is low. It's not a hippo. Okay. So what we can see now is these tests. Okay, so we spoke about a test on the differences. This was not a statistical test. This was just an example of the differences. We can talk about these two distributions. So here's a distribution of T0. Here's a distribution of Tx. Say all those means and their standard deviation. Okay, so this is one population. This is another population. We can see that these two means have very little overlap. There's a very strong test here. We're finding that we have really two very different populations. It's easy for me to reject the null hypothesis, right? So I have two things that are happening here. I have either the null hypothesis is wrong, okay, so I'm rejecting it. I'm rejecting the null hypothesis. Or my null hypothesis is right and I'm verifying it. Anyway, I have a test that is really clear-cut. Okay, I have two very different distributions. Or I can have a weak test where my two distributions are actually quite overlapping. I can't really tease apart the two populations. If this was the population of the weights of a hippo and the weights of an elephant, give me a number, any number, 5.9 tons. Okay, it must be an elephant, right? If this were the hippos and the elephants, give me a number, any number. Ooh, I don't know if it's an elephant or a hippo. Okay? So I have a weak test here. I have two, I'm finding it very hard to say whether the null hypothesis is right or wrong. Okay, I don't know if it's verified or rejected. So what are the risks that I'm taking? So why am I taking a p-value? What is the risk that I am getting it wrong? Is when, so if we look here, I had no overlap at all, right? So I have nothing in this distribution that matches that distribution. What I am allowing is a slight overlap. I have an area of false rejection. I can have overlap over here, and I could tell, have a risk here that I am saying, that's my 5%. I am saying this is not, I'm saying, you know what, this is an elephant, but actually it could be a hippo. And this is the area of false rejection. I am rejecting the null hypothesis, but there is a chance of getting it wrong. I don't want that chance to be larger than 5%. That's my p-value of 0.05. I also have an area of false verification, okay, which is this, that I'm saying the null hypothesis is wrong, but actually it is right. So same idea. So what am I applying my null hypothesis on? On the test variable, okay? We spoke about the difference. That was not a test variable. We usually measure something that's called a t, or something that's called a chi-squared. We're going to measure test statistic, and we'll see exactly which ones later, or an f. And I'm going to create the PDF of that test variable because I'm assuming normality, right? Or I'm assuming a t distribution. I know these distributions. I'm assuming the chi-square distribution. I'm assuming an f distribution. These distributions, I know that we spoke about them last week. You can refresh. They have certain parameters. So for the normal distributions, all we need to know is the mean to know where that center of mass lies on the number line, and the standard deviation, which determines how fat or skinny that function looks like, right? So we just need, so from that we can calculate our confidence intervals, and I think it was 95% of, so if the full integration is 1, we're looking at that 0.95 sum of the integration, either one-sided or two-sided. It's going to be two-sided. So we have a region of the hypothesis is true, so we can't reject H0 or is false. So H0 can be rejected. So those are the regions of true and false that depend on the PDF of the test variable. Okay, so this is how the PDF, the probability, the p-value comes into play. So we're going to start with an example of a t-test. Okay, the t-test is a test for differences in means. So we started talking about elephant weights, hippo weights. We can collect a population of elephants, a population of hippos, weigh them, and get the average, the mean weight of that population, which is an estimate of the true average. If I could measure all the elephants and all the hippos, of course I don't need stats, because I already know that. But because I'm only taking a subsample of the population, I need to understand what is a reasonable mean to get, right? So I can get from that subpopulation, I'm getting a certain mean, I have a certain standard deviation, I put it into the normal distribution, I can see the probability of getting different means, okay? If I, instead of taking that difference, use something called the t statistic, I can use the t-distribution and apply a student's t-test. I'll give some examples. So the t-test is a test for the mean. Okay, so I'm wanting to know, I apply a t-test when I want to know if is the mean different to, say, a number, or are means of two populations different to each other. Okay, so are boys taller than girls? Eucalypt, does this species of eucalypt use less water than that species of eucalypt on average? Okay, so those are the kinds of questions we're asking. Is there more calcium in this type of rock than in that type of rock? So what I have is a range of samples, okay, that I took from the population. In this case, two populations, one in red, one in black, or what I assume are two populations. That's my hypothesis. And I have some sort of X that I measure, elephant weights, hippo weights, amount of calcium in rocks. Okay, there's something, a variable I'm measuring, a continuous variable I'm measuring, and it has all sorts of values. Okay, and now I want to know, is the mean of this sample, of this population of samples different to the mean of this population? In this case, it's quite clear that I have a mean sitting somewhere here over here, and a mean sitting somewhere there. Okay. So here I have the delta mean, okay? And the delta mean is 0.1. Here I also have a delta mean of 0.1. You thought it was really clear? It wasn't actually. And here we have, what's different is the level of variance we have between the data sets. So if this is the standard deviation, remember the standard deviation around the mean, here it's quite low. and here it's much higher. Another issue is small sample size, of course. This makes it harder to tell apart two populations when I only have 30 points. I'm going to lose a lot of my power when we look at the T equation. You'll see that N, the number in your population, is there. Okay, so we need to have, it's part of the test. Here we have a lot more confidence in what we're saying once we have big sample sizes, right? We have a clearer indication of what the mean truly is. So even though we have the same difference in mean, we have the same spread around the mean, we have a lot more confidence in what the mean truly is in a population that's been sampled more than 3 times. Okay, so these are why we need a statistical test, because things are not straightforward. And when I look at the student t-test, we say, here are the differences in the means. Here is the standard deviation, what the spread is around the mean. Of course, a sample that is not spread around the mean so much, we have a higher confidence in our mean value than in normal distribution that goes for miles, right? So, and then multiplied by the square root of the number of samples. More samples, the higher the t. Okay, so it's easier to tell apart. So a bigger t is an indication of bigger differences between our populations. So what are we assuming here? We see the mean and the standard deviation. Those are the 2 parameters of the normal distribution. Okay, so we are assuming our sample data is following a normal PDF. To do that, another thing which we always assume is that the data is taken randomly, independent, unconditional, right? Like we did not just select the hippos that are too big to run away, right? So t-values get larger. As t-values get larger, we are suggesting a significant difference in mean, okay? Because t-values get larger for a few reasons, right? If we look mathematically, we have the delta u, mu here at the top. This is a bigger number, this is a bigger number. So a bigger t suggests a bigger difference in the means. Okay, so our means are further apart than, you know, suggesting that the true difference between those 2 populations, but this is what we're after. T-values are large when the signal-to-noise ratio is large. Okay, so here's my signal, the difference in the mean. Here's my noise, is the standard deviation. That I can get a very big difference in the mean, but like we saw before, if they're spread all over the place, it's very hard to detect. And I can have t-values that are large when the number of samples are large, which is why it's always good to sample a good number of samples. It makes it easier to detect differences if they exist. If the differences don't exist, you still, you know, they still don't exist, right? But if they do exist, it's harder to get that false negative or false positive if you have a large number of samples. So let's look at the t-distribution. The t-distribution, the link to the number of samples comes in the shape of the distribution. Okay, so these are the degrees of freedom. df comes from number of samples. And one of the degrees of freedom are that usually it's the number of samples minus 1. Okay, so we have the, because if I have 3 samples, I have 2 degrees of freedom. I can pick 1, 2, the third one is what's left. I have to take it, right? So that I have no freedom in choosing that one. So the degrees of freedom are the number of samples minus 1. So the t-distribution looks very similar to the normal PDF. We said it's just a bit, there's a bit of a high kurtosis here. And when we say, when we calculate the t value, which again came from the n, came from the difference in means, came from the standard deviation around the mean, this is a simple calculation to get a t statistic, something that represents the difference between populations. And we already know that above 2, So a t statistic can have a range of numbers, and above 2, they kind of pass the 95% p-value. Okay, so the chance of getting this, if I look at it in a cumulative t-distribution function, by 2, I've reached about 95%, depending on the n. So here's the basic form of the t-test. There's another thing we can apply instead of the standard deviation and the square root of the population size. We can use a statistic called standard error, which is, so basically mathematically, I've just replaced this with this number here, which is the standard deviation divided by the square root of the population. That's called standard error. So there's standard deviation, this thing, which is the square root of the variance. And there's standard error, which is another mathematical iteration of error. And it's just like a change here. I mean, like it's just replacement. Okay, so I've done nothing from this step to this step except all these numbers something else. So here are some examples of what t's I can calculate. So here we have a difference in mean, that's always 0.1, right? We have standard deviations that vary widely, and we have population sizes that vary widely between these plots. And from that, I can calculate different t's. So there are places here where I can see t's are getting pretty high. That's where I have little spread around the mean. That's where I have high population sizes. I have these two t's. So, of course, the difference in the mean is actually the same everywhere I look, but I cannot detect the difference in the mean. In these two, I just don't have enough confidence. The p-values are not going to be below 0.05. The chance of me getting a t equals 0.3 is actually quite high. So there are a few examples for the sample t-test, and we'll talk about those in the next lecture. So we can use it to test our sample mean versus some theoretical mean. So that's called a one sample t-test. I really just have one sample of the population. I want to know, I go to the supermarket, right? We do this all the time, by the way. I go to the supermarket and I buy bread. And the bakery makes the bread. It's better than the one that comes in the bag. I go to the bakery, I get a loaf of bread. And you know what? They vary a lot in size. And every now and again, an inspector would come and buy 10 loaves of bread. Because there's a minimum size they need to be at, right? So I have some theoretical mean. The bread should weigh 580 grams, say. And you can measure the population of bread at Coles or Woolies or IGA. I mean, I'm not taking sides here, and compare that to a theoretical mean. Okay? And that would be a one sample t-test. I can measure elephants versus hippos, sample A versus sample B. Or I can measure another thing called the pair t-test, and we'll come to that when we get to it.